All right, this is our final tutorial. I can't believe that we made it this far. So in this video, we'll cover some basics about downloading and using Neon data in R. So the first thing you want to do is open up our studio. We want a new project inside of a new directory, new project. And the directory name, I'm going to call this Neon Project. And this is the folder that you'll end up submitting to me. We'll create project. It takes a minute. And now I can see that I'm in this Neon Project folder. Here's that .rproj file. And now I want a script. And I'm going to call this something like Neon Data. And I also want a new folder called Data. And this is the folder where you'll download and save your Neon data. So I'm going to demonstrate two ways of downloading Neon data. The first is through the website, and the second is through R. So let me bring up the Neon homepage, and we're going to navigate to the data portal. This should feel familiar. I'm going to, once you know the data product that you're working with, instead of instead of using the Explore data products to browse all of the available data products, what you can do is copy and paste your DP number, your data product number. So I'm going to copy and paste this data product number. And I'm going to select enter, and it'll bring up the specific data product that you're interested in. This is one example, you'll have others. And you want to navigate to download data, and it'll first ask you what sites and dates do you want. So I'm working with rodent-borne pathogen status data as our example. And I'm interested in how pathogen status changes over time. Maybe in warmer years, there's higher pathogens. So I want to find a single site where there's been multiple years of sampling. So you can see, this site, there's only been 3 years of sampling. In this site, there's only been 1 year. So I want to find a site that has kind of multiple years. So I've found this site 1, 2, 3, 4, 5, 6 years of sampling. I'm going to go ahead and select this. This is the Smithsonian Conservation Biology Institute in Virginia. So it has some relevance to us in Richmond. And I'm interested in all the dates, so I'm not going to change those. And I do want to include documentation because remember, it'll have all those metadata files, including PDFs about the sampling protocol. And I'm not very familiar with how pathogen status is collected, so I do want to include all the relevant documents. And I'm going to select next. And I'm going to select the basic package. The expanded package includes data checks and quality control things that, for our purpose, we won't be using. So I'm going to select basic, and it'll automatically take me to the next page, and I agree, and it automatically takes me to the next page when I select the box. And everything's looking good, so I'm going to download the data. So I'm going to save it, and I downloaded it previously, so I'm going to just change the name. And so that'll download as a zip file. And actually, I need to save it. I need to save it in the data folder for the Neon project. That's where you want to save it. So now I can save it as the original name. It's in my Neon project folder that I just created at the beginning of this video, inside of the data folder that I created inside of RStudio. And I'm going to save. So that's the zip folder. And now it should appear in here as a .zip file. So that's the first way of downloading the data. And in a minute, we'll see the second way of downloading data directly from RStudio. So let's look at how we would open these files. And maybe we should look at the raw files first. So inside this zip folder, now there's another zip folder nested inside with this really long string file name, and it has the domain, the site itself, SEBI, the data product, and the year and month of sampling. So this was sampling for pathogens in small mammals in their small mammal traps in May 2014, June 2014, July 2014. So every single month has its own folder. And that's not really useful because you want to work with one very large data frame. So R and Neon has functions and packages that make it really easy to combine these files. We can also see the data, the metadata files as well. And yeah, there's a lot of information about the sampling and some background information about each data product. So let's start working with our data in R. The first thing we need to do is install a bunch of packages called Neon Utilities. And there's a bunch here, ggplot2. We've seen before. Actually, we've installed a bunch of these before, so we don't need to. So we need to install that packages for Neon Utilities. I'm going to go ahead and run that. And now I'm going to start working on the script while that's downloading. So we need to load the libraries, Neon Utilities, library ggplot2, library dplyr, and library tidyr. And I think we've installed tidyr. If not, you can use the install.packages and put tidyr in quotation marks and install that as well. So I'm going to load the libraries. Did I load Neon Utilities? Yeah. Okay, and that's just a warning message that it was built under a particular version. And it should work fine for the version that we have, 4.02. So I guess there's an even newer version of R, 4.03, but it shouldn't cause any big issues here. Okay, so I've got my required libraries loaded, and because I'm using a project, right, because I'm using an R project, my working directory is set to this folder, to the Neon project folder. If you want to check, you can type get wd. So our get working directory is pointing to the Neon underscore project folder. So that's what we want. So the first thing we need to do is unzip and join the files in the downloaded zip file that we placed in this data folder, this whatever your data product is. And we'll use the function in this Neon Utilities package that was created specifically to work with Neon data, stack by table, and then we need to tell it where the data is and what the data, what the zip folder is called. So it's in our data folder, and it's neon pathogens -rodent.zip. And I'm going to run this, and I don't know why. And it might take a minute. So, okay, so now finished, stacked 1 data tables and 3 metadata tables, and all unzipped monthly data folders have been removed. So now we have inside of our data folder, we have this new folder, the same name as our zip file. And inside that folder is the metadata and a new folder called stacked files. And so in the stacked files folder, we have a few tables, the variables, some sort of validation, and this file, which is the primary file. So then we would need to use our read.csv function. I create an object in which to import this data. Read.csv, I need to tell R that it's in the data folder and the file is called lead testing.csv. If you're using a different data product, then you'll need to open each one of these to figure out which one is your main data file. And it should be pretty obvious, because when you open up these, this will be a list of the column names and their description. This might be a description of any data quality issues. And this might be some sort of codes, whereas whatever your main file is called, it'll look very similar to the data frames that we've been working with. So read.csv, it's in the data folder. It's called rbt underscore blood testing. And no such file or directory exists because it's not just in the data folder. It is in this newly created folder inside stacked files. So data, neon pathogens, -rodent, stacked files. I've got a case, large case here, uppercase. And then, okay, so now it should work. And if I wanted to view that file, now I've got this data frame imported into R, and it should remind you of the kind of data that we have been working with for the small mammal traps weeks ago now. All right, so that was a demonstration of how you would download data from the Neon data portal and import it into R. Import the zipped folder, use stack by table to unzip everything, combine magically all of the monthly folders, so you don't have to do that by hand, and then import the combined file into R. So then with this, then you would do maybe make a ggplot or select specific filters, use dplyr to group by specific dates. So we'll see an example of that later on. In this next example, I want to demonstrate how you would download Neon data directly in R. To download Neon data directly in R, we need a function called load by product. And you can see that there's many different arguments in here. The first one is the data product ID, the site that you're interested in, start date, end date, package equals basic, some of those things that we were selecting when we were using the data portal. So now we would have to specify those in this load by product function. So let's see an example with a different data product ID. Let's use dpid equals dp1.198.001. This is the woody vegetation structure data. And let's download it for SCBI because that's the side where the pathogen data came from. Maybe we want to relate the two together. And a few other things we need to know. We want package equals basic, and we want to set check size equals true. So check size asks if it's set to true, then R will ask you if it's okay to approve the total file size before downloading. And if it's false, then it won't ask you. And this is useful if you're working with really large amounts of data. And I always like to set it to true because sometimes I don't realize how big the data set is that I'm downloading, and my computer is way too old to handle it. So check.size equals true. Load by product, we got the DPID, the site, and check size equals true. And it might take a little bit to download, and it'll ask you, because you had checked size equals true, where we get this question: continue will download files approximately 4 megabytes. Do you want to proceed, yes or no? So I'll type in a yes. I don't see the Y. Download halted. Do you want to proceed? I put a Y there. Maybe I need to put a Y here. There it goes. And for some reason, R didn't like the package equals expanded and check size equals true, so I deleted those, and it seemed to download. And I didn't store this in an object, so it printed the output in my console, which is exactly the opposite of what I wanted. So I'll give this a name called veg_structure. And let's see if this works again. So I need to select Y, and hopefully it'll download the files and store them in this veg structure object that I created. Now we see the veg structure in our environment here. Right? It's a list of 8. So we can use things like names and see all of the names of the files. And look how similar they were to the stacked files from our pathogen data, right? They all have the categorical, the README, validation variables, and then they have these these files, which are specific to woody vegetation. So these are all the individuals, maybe their tag number, individual trees and shrubs, their tag number, and these are other information that might be useful depending on the type of question you're interested in. We can also view Vegstra. Let's see, per plot per year. So let's view this one. So we have the plot ID, the longitude, latitude, elevation, total sampled area, and other information. Now, Vegstra, if you look at the structure of this Vegstra object, it's this complex list. I don't think we've worked with lists, but lists can be a bunch of different data types in a single object. So in veg structure, it consists of multiple data frames that are nested within this single object. If you prefer to extract each table from the list and work with it as an independent object, we can use the function called list2end, and we need to call something, we need to tell R to extract list to our global environment. That's what this represents. And it'll extract all the list elements to our global environment. So let's go ahead and do that. And now we see automatically all the files that were inside of our list. And they're in our global environment, so we haven't actually saved them in our data file. And maybe you're working with big data sets, so you don't want to re-download. So you want to be able to close R and come back to these data locally, and we can use the write.csv function to write the VST apparent individual, which if we look at this, right, it has this similar format. The site, plot ID, growth form, whether it's a tree or shrub, the diameter and the height of the tree, and at the end, I believe it should have, like, I'm looking for an individual ID that I would need to merge with the other file called mapping and tagging, which should also have individual ID, the same column name, but in this one, it contains the scientific name. So if I wanted to analyze or map maybe the diameters of all the trees by different species, I would need to merge these two files by individual ID, because that is the column that the two data frames share to be able to identify what species are these rows and observations. So let's write these files. And so we need to tell R which file that we're interested in and then where to save it. So I'm going to save it in our data folder. And I want to maybe create a new folder called Neon Woody Vegetation. And then I would save it in that folder. Vegetation, and I need to give it a name, VST, apparent individual.csv. And now that file appears in the folder. So I'm going to do this for the other files, VST, mapping and tagging. And I'm going to copy and paste to avoid typos. And then I might also do this for the variables data, mapping and tagging. I noticed a typo there. I need to designate .csv. All right, now run this and I'll run that. And now, because I didn't designate the .csv, I noticed that mistake. It wrote this file without without kind of this suffix. So I'm going to delete it because it probably won't be able to open. Okay, in this next half of the video, what I want to demonstrate is the level of detail that is expected for your NEON project. So this would be a great example to follow if you're wondering kind of what level of detail to build into your NEON project. So I'm going to take you from downloading data to creating a ggplot. And this could be my NEON project that I were to submit. So let's start by downloading the data of interest. In this example, we're going to be using air temperature that's collected by NEON at the same site, SCBI. And air temperature is collected at every single minute and every 30 minutes. And every single minute, air temperature for every single minute, every single day, for every single year is a lot of data. So we're going to download the 30-minute intervals for a single year. So I'm going to create this object called maybe air temp. I'm going to use the load byproduct function, dpids dp1 dot 402.001, our site SCBI, start date. I definitely don't want all the data because that's a lot of data. And this computer that I'm working on is really old, but it still works, so that's good. All right, so I'm going to start from 2018, January of 2018 to December of 2018, and that's inclusive, so it'll include January, all the air temperature that was collected in January and December, as well as everything in between. And I want to designate the average 30 minutes. And I'm going to check that size equals false. And I'm going to go ahead and run that. And it might take a minute to download all the files, about 8 megabytes. Okay, the downloaded files are in my global environment as air temperature, but remember that I want them stored in my data folder. So I want to use the stack by table function, and No, it's not stacked by table. What we need is the list to environment because we've downloaded the data within R, so R automatically unzips all the monthly data folders and combines them. So air temp is a list. What I want is to extract that list and store all the elements in our environment. So now I've got all of these. Single air temperature, 30 minutes. And there are 4 new files. There's this variables 00002 that checks out with this kind of data, part of the data product ID. There's the data itself, that's single aspirated air temperature at 30-minute intervals, different sensor positions. So that's the coordinates of each different sensor, and a README file with that a shared part of the data product ID. So we want to work with the individual files. So we unlisted the air temp object that we created. And now we can look at what is the structure of the data itself. So let's look at the structure of this single air aspirated temperature at 30 minutes. And we can view it. And it'll look familiar, right? It'll have that same kind of structure and column names. So we've got a mean, minimum, maximum, start date time, and end date time. And when I'm looking at the structure, I can see that the date is being recognized by R as a date time. And there's numeric columns, character columns. Okay. Things to be aware of when working with your data is something called final QF. So this is the final quality flag. So a pass of this quality check is 0 when the data checks out, meets all the criteria, and it fails when final QF is equal to 1. So let's see if we have any data with a quality flag. So we would do this by asking R, is this single air aspirated temperature 30-minute data frame and a specific column equal to 1, but we don't want to produce a bunch of true, false. We want R to sum up all of the instances where this condition is met, where final QF has a value of 1. So let's run this, and there are 20,000 rows where the quality flag is equal to 1. And don't be too alarmed by this. Remember, this is data for 30 minutes every day, all day, for an entire year. So if we look at the dimensions of this data frame, right, there's 87,000 data rows, and of those, 20,000 have a quality flag. So to demonstrate, let's keep the flag data for now. You'll want to remove these, and we'll do that in a minute. So what about null data? These are things that you're going to want to check for because they'll cause errors later on. So we can do this by asking our is.na, this data frame for temp single mean. And that's why the metadata is really important to understand what each column actually is and where your data is. So not only do we want to ask, is there an NA in this column, but we want to sum up the number of rows where is that NA equals true for this column. And so we've got 19,000 rows where there's an NA for the column that we're interested in. And the reason why it's important to understand the data quality with final QF and is there NAs in the column of interest, because it will cause issues when you're calculating things like the mean or if you're summing the values. So remember, a mean for a column with NA is NA because R doesn't know how to calculate the mean for a value of NA. So it spits back an NA. So we need to tell R to either drop those NAs or remove them. So let's create a new data frame without NAs. Let's use the same naming format and add a no NA to the end. And let's call our original, use our dplyr pipes, and we can use a new function we haven't seen before called drop underscore NA. And we want to drop temp single mean. So this new data frame is going to have all of the rows where there is not an NA in this column. So it'll delete the rows with an NA in temp single mean. And now we can look at the dimensions of this new data frame, and it has 67,000 rows. So that would be 87,000, this number minus this number. Right, so all those rows with NAs in this column was deleted. Now, if we repeated this for our new data frame, right, where we were asking, are there NAs in this column? Sum them all up. Now we get a value of 0. So we know that it worked. For your data set, you're going to want to do additional analyses. You might want to calculate the mean by species, but you definitely should do additional analyses. For this demonstration, I'm going to keep it fairly simple for this part, right? So this is the meat of your project, and this is what I want you to expand on. Once you've expanded on your analyses and you're ready to plot your data. So one of the expectations for this project is that you produce this kind of beautiful data visualization. So now we're ready to plot temp data. Let's store this plot in an object called temp plot, and we'll call ggplot. And let's plot our raw data that we didn't manipulate or remove NA values so we can see why they're an issue. So let's do for our x-axis, our start date time, and our y-axis temp single mean. Notice how if I put the arguments in the order that R expects them, I don't have to label them as x equals or y equals. Sometimes that helps reduce the amount of code, but if you're starting out or passing your R code along to someone else who doesn't have as much experience in R as you do now, then it helps them understand what the code is doing. And okay, so we've told R what the data that we're interested in plotting, but we haven't given it a geometry. So let's do a scatter plot. And let's modify the title. And I'll have to check the metadata to see what units is the temperature in. So that is in Celsius. I read the metadata. And those are my X and Y labels. And I want to definitely modify the theme. So I want to modify the plot title, the text element. I want line height equals this, space. I want bold, tide, and I want a fairly larger size. You can play around with the different values and use the ggplot resources to look at all the different ways you can customize your plot, make it nice and beautiful. Element, and I want the other text size to be a large size. I'm trying to make this really nice. And it might take a minute because it's a lot of data, right? We're talking about 87,000 data points. And it's not plotting because I stored it in an object called templot. So in order to plot it, I need to call that object templot. And I get a few warnings, something about the font family. I changed something in my fonts, so R didn't like that, but it was a warning. It wasn't too serious of an error because the plot is still plotted. So I would have to look at this larger to see what's going on. So it took a little while to plot because there's some 80,000 observations, and what patterns, two things stand out to you, right? That this kind of variation up and down, that's probably nighttime and daytime, variation in temperature, and we also see these kind of weird points. These are probably, when the sensor restarted or there was some error in the sensor reading, and that's why we need to remove data that are flagged with those quality flags. And right now we're looking at all of the data points, and it's kind of hard to see even when I put this up to full screen. Right, it's kind of hard to make out the individual variations. So instead of plotting every 30 minutes, I might want to aggregate those data to a single day. So there's just one day for each day instead of, or one data point for each day instead of however many data points there are in 24 hours divided by 30 minutes. So you'll definitely want to go through this process of considering, how could I improve a visualization like this? Is 80,000 data points necessary to convey what I'm trying to convey? No, because what I'm trying to convey is this kind of yearly variation in air temperature. And so having temperature for every 30 minutes, every day for a whole year, it distorts that message. So let's start out by removing the flag data and aggregating to a daily mean. So let's subset and add C to name for clean data, where there's none of the quality flags that are equal to 1. So let's call this and add a C. So this will be our clean data. So let's filter our original data, our min underscore no NAs, where our quality flag final QF is equal to 0. So we want to work with our no NAs, and then from the no NA file, we want all the rows where the quality flag was equal to 0, because that's indicates that there are no errors. So I'm going to run this, and we can see if this worked by sum 30-minute C for clean, final QF equals to 1. So let's see if there were any rows with a quality flag, and there are 0. So now we can plot the clean data. And I'm going to copy and paste from above, plot clean temp data. And I'll expand this, make it a little bit easier to see. Instead of 30-minute, I want to do 30-minute C. And everything else stays the same. So I'll run this and then plot it. And now those weird values should be removed. So I'll zoom, and we can see how we remove those kind of weird data points. And it did help a little bit with the kind of overall look of the graph, but it's still, right, there's still kind of a lot of data points clustered together, making it hard to visualize that pattern. So now let's aggregate data by day. And we've aggregated, remember we've used the group by function, so we'll do that here. Let's convert to date. Let's convert our start date time to date, because it's a little bit easier to work with. So let's create a new column in our cleaned data frame, this sat 30 min C, and we'll create a new column called date. And inside that column, we'll use this function called asDate, which pulls out the date from a date column. So our start date time had both date and time, and we want date by itself. And that's what this asDate function does. And let's see if it works. 30 min C, we should have a new date column at the very end, and R recognizes it as a date column. So that's great. Now let's calculate the max of the mean temperature each day. So let's create an object called temp day from our cleaned air temperature. So let's take our cleaned air temperature, use those pipes, then group by date column, then, oh my gosh, what did I do? I must have hit some keyboard shortcut. And so if you ever that ever happens, this little icon here can return you to normal. All right, so take our clean data, then group by date, then let's use a new function called distinct date. So this will keep distinct date but we want to keep all equals true. And remember, because we converted this column to date, there's going to be 24 hours divided by 30 minutes, right? For a single day, there's going to be multiple rows. So we're telling R that we want to keep a distinct date, but keep all of the rows, because in this next step, we're going to do something with them. So in this next step, we're going to use that mutate to calculate a new column called day max equals max of the column temp single mean. So this is the maximum daily temperature. And to go through what we're doing, we're picking out from our clean data, then grouping by date. And there's hundreds of, let's see, if there's 30 minutes, if 1 hour has two 30-minute recordings, then 20, so there should be 48 rows for each date, for each unique day, like month and day. And we're telling R to keep all of the rows even though they have the same date, because we want to calculate the maximum temperature for each day in this new column. All right, so I'm going to run that. And now we can plot the cleaned up data temperature. So I am going to copy and paste below. And I need to, instead of this day, I need temp day, this object we created. I want the column date to be my x-axis, and my y-axis, I want day max. And I want to keep the scatter plot. And now this is daily max air temperature. X label, I want to be date, and Y label is the same. I'll keep all of this the same. And I want to change this to like temp day max, so I don't write over my, and that's because I didn't run it. So I'll run that, and then I'll run this, and now I'll zoom. And so look at the difference. So now we can see the individual data points for a single day. So this is the maximum temperature for January 1st. And this is the maximum temperature for December 31st. And so that makes it a lot easier to see this kind of seasonal variation of maximum temperature in a single year. And that's a huge difference over the previous plot. So when you're creating your graph, ask yourself, what do we gain by plotting a specific subset of the data, right? What do we lose over the 30-minute intervals, right? And ask yourself whether that aligns with what you're trying to convey. I might even make this even nicer by maybe using a different theme. You all know I don't like that gray background, but it's personal preference. And I might even put kind of a geom smooth, and I think it'll automatically detect the smooth formula there. Right, this kind of like regression line. So these are the types of details that you should consider when working with your own data. make a graph that you would expect to see in kind of an article online or newspaper. That's something you can share um, with your professors that you work with, or something that this is something that you can take when you're working in a lab in the future. And yeah, really have fun with it. I hope you enjoy customizing your ggplot, playing around with the different colors and the size of the data points. So this is the kind of level of complexity that I expect in your Neon Data project, right? I want to see you be able to import data in R, remove the NAs. I want you to be able to understand the metadata enough that you know how to clean your data for those trouble rows, for those trouble entries. And I want you to be able to, use dplyr to calculate something, a new variable, to aggregate your data by groups, by species, by dates. Here we're calculating a new value, right? The maximum daily temperature. And then I want you to be able to use ggplot, and I want to see that you can use all the different kind of arguments here. So take a look at the rubric. If you have questions, let me know, and have fun with it.